Morning, everybody. Let's go ahead and get started. So, let's just get the elephant out of the room and talk about the exam redo. You all have the instructions for that. Extra credit requires extra effort. Okay, so my philosophy is I'd rather you learn than worrying about points. So I want you to redo your exams for half your missed points. I've given you instructions in Canvas in that announcement. You have to follow those explicitly to get your half missed credit. There's a reason to that madness, okay? And it has to do with being able to follow rules, because organic chemistry is about being able to follow the rules, okay? So each question has to be worked on its own page. You have to handwrite out the whole question, all of the answer choices. You have to circle the correct one. You have to tell me what page in the book or pages in the book where the topic was covered. And then you have to write a little bit of a paragraph on what about that topic or that question, was confusing to you or caused you some issues. You will do that for each and every problem that you missed. And then you will write that one-page reflection, self-reflection on your study habits, and write it as if you're talking to yourself. Okay? It's not what I want to hear. It's what you need to hear from yourself about after this first experience with an organic chemistry exam. Are your study habits sufficient? Where did you do well? Where did you not do well? And it needs to be about a page in length. Okay? If it's anything, if it's a half page, it's too short, okay? If it's around, but it needs to be pretty close to a full page, okay? So now I'm not going to count the words. I'm not going to sit there and, measure. Pardon?
Is it double spaced?
I can't remember what I wrote in there. Single spaced? Yeah. So it needs to be a good self-reflection. All right. So we're going to finish chapter 5 today. So we're going to do a quick review of where we're at, and then we're going to finish up the new material. So what was chapter 5 all about? Okay, we're talking about reaction mechanisms. What particular reaction are we talking about? Addition, right? So we are adding things to alkenes. So I'm just going to draw an alkene. Okay, so just a basic alkene, and we've talked about being able to add things across that carbon-carbon double bond. What have we added across the carbon-carbon double bond so far?
HX.
All right, so we can add HX. Oops. HX, where X can be what? Okay, and how do we add HX across the double bond?
Break the double bond into single bond.
Okay, where does the H go? Okay, so it's going to go to this carbon, right? So we're adding H and X across the double bond. Whose rule is that? Markovnikov's rule, right? So this is Markovnikov addition. Okay, what else can we add that did we talk about? I think I heard it earlier.
Water.
X2.
X2, right? Where X is what?
BR is here.
Yeah, bromine or chlorine. So we can add X across the double bond. We'll learn more about that mechanism today. What else did we talk about?
Water.
Water. Just water, or do I need something else? I need a little bit of a strong acid, and we talked about H2SO4. In fact, it's a catalytic amount of acid, means you just have to add a little bit, not a whole lot. And so how does that add?
H and OH.
And how? Where does the H go?
You're right.
Okay, so the most, yep. And OH, so that's the water being added across the bottom. Again, that's following Markovnikov's rule, right? All right. And then we talked about the mechanisms of these additions, right? And so if we think about adding HX across the carbon-carbon double bond, what's the first step?
The
Breaking the pi bond, okay, and what happens with those electrons?
goes to the hydrogen.
Okay, so they go to the hydrogen, then what?
The bond between hydrogen and X breaks.
All right, and now, which carbon does the H go to?
The one that has more carbon, more hydrogen.
More hydrogen, right? So it's going to go here. And what does that put on this carbon for right now?
Plus
Plus
positive charge.
positive charge, right? We call that a
Carbocation.
carbocation, right? This is an intermediate, right? It forms, we get it? Now what happens?
The X impacts the carbon atom.
And so this is a two-step mechanism, right? So this is the mechanism for the addition of HX across a carbon-carbon double bond. It does follow Markovnikov's rule, right? We talked about the energy diagram for that. We talked about intermediates last time. If we look at this piece of the mechanism, what is the Lewis acid and the Lewis base in the first step? What is the alkene?
Lewis base.
It's a Lewis base because it's donating a pair of electrons, right? So this is the
Lewis acid.
Lewis acid. In this step, what is the Lewis acid and the Lewis base?
The X is the base.
Yep, so the X minus is the Lewis base. It's donating a pair of electrons to the carbocation, so the carbocation is the
Lewis acid.
Lewis acid. Right? So being able to identify the Lewis acids and Lewis bases is very important in these types of reaction mechanisms. Okay? So, today we're going to continue on by talking about how we can add X2 to an alkene. We're going to talk briefly about carbocation rearrangements. Carbocations are intermediates, but they're not stable, and so they can do some really weird chemistry. We're not going to belabor the point of carbocations, but I want you to be familiar with it. We're then going to talk about hydroboration oxidation, which is another way essentially to add water to a carbon-carbon double bond. And you might be asking, why do I need two ways to add water to a carbon-carbon double bond? And we'll talk about that today. And then we're going to talk about reductions of alkenes and alkynes, how we can convert alkenes to alkanes and alkynes to alkanes and alkenes. So we'll talk a little bit about that today as well. So we learned in previous lectures, right, that the addition chemistry is pretty straightforward in terms of how we think about it, right? We're going to break that pi bond, and we're going to add X2 across the carbon-carbon double bond and make these new carbon X single bonds, right? What is stronger, a pi bond or a sigma bond? Sigma bonds, right? So I'm breaking a weak pi bond, but I'm gaining two strong sigma bonds. So the reaction should go to completion, right? We always want to favor stronger bonds, right? So I'm sacrificing a weak pi bond, but I'm gaining two strong sigma bonds. And we call this molecule a dihalide. Vicinal just means that they're side by side, okay? Don't worry so much about that. So we've added X2 across the carbon-carbon double bond. This only works for chlorine and bromine. If you take an alkene and you put F2 in there with it, it goes boom. It will explode on you, okay? Very reactive. So not terribly healthy for you. Iodine will not do this reaction either. It will add, but it then comes and falls apart back to iodine and alkene, okay? And we don't need to go into the details for that. So for all practical purposes, the only way to make these vicinal dihalides is through the addition of either chlorine or bromine, okay? So here are some examples, right? You can take, what would we name this molecule? Ethene, is the correct name, but it also has a common name, ethylene. Okay, so you all might remember some plastics are called polyethylene. They actually take this molecule and polymerize it and make bigger molecules.
Memorize the common names, because I noticed there was
If you know the systematic names, we're good. Yeah, we're going to be good. So I can add chlorine across the carbon-carbon double bond, and I get this dichloroethane. Okay, how would you name the product? Would you just call it dichloroethane? 1,2 dichloroethane, right? Because in theory, one could imagine having both chlorines on the same carbon. Not from this reaction, but one could imagine that, right? What's the name of this alkene? Cyclohexene. Do I need a number? I don't need a number because it would, until we put some constituents, it just doesn't make any sense to. But if you called it 1-cyclohexene, it wouldn't be incorrect. It would just be redundant, right? So we're adding bromine across the carbon-carbon double bond, and we're getting this dihalide. How would we name this product?
1,2-bromo.
Close. Yeah, 1,2-dibromo cyclohexane.
Hexane.
Right. I don't know that I heard that. But yeah, that's the reaction that we're talking about. Okay? Now, the mechanism for this is pretty interesting. When you take a anything that contains a carbon-carbon double bond and you add a halogen to it, it goes through this so-called bridged polonium ion. It's kind of interesting, right? It's kind of an interesting little structure. Does that look particularly stable to you?
Yeah.
Why not? What do we know about the halogens? Are they electronegative or electropositive? They're electronegative, which means what?
They won't more than
They want electrons, right? And we're putting a positive charge on something that's electronegative. Is that a good thing or a bad thing?
makes it unstable.
Makes it unstable, right? Makes it unstable. But nonetheless, it exists, right? But what would you predict its reactivity to be? Non-reactive or very reactive? It is very reactive. It doesn't last very long, right? And so what happens is you form this so-called polonium ion, and then the other halogen comes in and attacks that carbon to make a new carbon-halogen bond and breaks this carbon-halogen bond, okay? And so that's how you end up with the dihalide, okay? So what does that mean? That means that this bond that's being formed here has to be on the opposite side of the molecule of the other halogen. So these halogens are going to be on opposite sides of this plane, okay? This does not go through a carbocation intermediate. It's not like this, okay? It is not like this at all. There is no carbocation in this reaction, okay? And so if you think about it, carbocations are also unstable, right? But actually this is a little more stable because everything here has an octet. The octet rule is satisfied here in this intermediate, okay? And so even though you're putting a positive charge on the X, or bromine or chlorine, whatever it might be, everything in this molecule, or this intermediate, I should say, has an octet of electrons. So that's why it goes through the polonium bridged ion, if you will, okay? So, let's break up into some groups. Let's take 3 or 4 minutes. I want you all to work these 2 problems. Go on, get in your groups. Yeah.
Oh, no, sorry.
We're working. You all 3 can work together if you want.
Right. Yeah. Then, because you had a text from this side, maybe it's like two places. Yes, so this makes sense if this is here.
All right. Let's work this first one together. What's going to happen? I know I've got an alkene and I know I've got a halogen, so I know I'm going to add X2 across that carbon-carbon double bond. I know what my end product is going to be. Wherever that carbon-carbon double bond is going to be, that's where my new halogens are going to be, right? Or wherever the double bond is where my new carbon-halogen bonds is going to be. But let's work through the mechanism. So what's going to happen?
Double bond word.
Okay, double bond breaks.
Goes to
Attacks one of the bromines. Bromine can only have 8 electrons around it, right? So this bromine bond has to break. But bromine also has lone pairs of electrons around it, right? And so instead of generating a carbocation, these electrons also come around and form a bond with the other carbon. That's why we're showing these 3 arrows all at the same time. And so what I'm going to get as an intermediate is what?
The two bromines on where the double bond was.
Well, that's the final product, the intermediate.
one bromine attached to one.
All right, so I'm going to have that 3-membered, or that triangle, right, where bromine's going to be at the top, and it's going to be a halonium ion, right? And I'm going to just draw this with a wedge, indicating that it's coming out of the plane of the board. We'll talk more about that later, okay? But I can't make, and you can use your model kits, try to make a bond that goes on the other side of a 3-membered ring, you'll find that you can't do it. You will break your model kit, okay? These have to be on the same side. These 2 bonds have to be on the same side of the molecule, okay? Now what happens?
The long bromine attacks the other bonds.
Yeah, you're going to learn that organic chemistry is a violent sport. We attack a lot of things, okay? So bromide attacks that carbon and breaks that carbon-bromine bond. And so this means that it has to come in on the other side of the board. And so what we get is a product that dashed wedge means that the bromine's on the back side of the board. Okay? How would I name that?
The intermediate.
The final product.
1,2 dibromo cyclopentane.
1,2 dibromo cyclopentane. We're almost there. I got to add one more word. Trans. The bromines are trans to one another. If all 5 atoms of this are in the plane of the board, one's coming out, one's going back. This is trans. 1,2 dibromo cyclopentane. If I had drawn it like this, that too is 1,2 dibromo cyclopentane. But that would be what? Cis. And I can't account for this through this mechanism. You don't form any of this in this reaction, only the trans. Okay? Yes, sir.
Can you explain that a little more? I'm not following you on
Which piece?
that. Being trans.
All right. So the way I have this drawn, right, will you agree that the bromine's out of the plane of the board? All right. Now, bromine, which I haven't drawn here, also has other lone pairs of electrons around it, right? And so this bromine is going to attack on the other side of the molecule. It has to, because it's got to break one of these bonds. And the only way to do that is to attack on the other side to break the bond. Okay?
So does that mean they're always gonna be trans?
Always. This is a very specific reaction. Anytime you add halogen across a carbon-carbon double bond through this mechanism, you will get a trans product.
The X2 mechanism is always gonna be trans.
Yep, it is always going to be trans. Okay? And so this has to come in from the other side of the board, and that's why I draw it like this. So this bromine right here is the bromine from the polonium ion. This bromine is the bromine from the bromide. Does that help?
How do we know which one's going forward and which one's going back? Like, how did you,
I arbitrarily
positive and negative?
I arbitrarily assigned it that way. We'll talk more about this in chapter 6, so don't worry too much about it. But I could have just as easily drawn this with the dashed wedges and then drawn the bromide coming in from this side, and I would have ended up with the same product. Okay? And in fact, both would occur. So what do we get in the last one? How would we name that molecule? That's the product, right? What is that?
1,2-dichloro, hexane and trans.
All right, do I have enough carbon? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So what is it? It's hexane, right?
Yeah. Trans 3,4-dichloro hexane.
And no matter which way I go, it's going to be the same numbering system, right? So it's 3,4-dichloro hexane. And you all say it's trans. I agree that it added trans, but why do I not have to write trans here? I don't have to write trans here. Why? Pardon? The triangle's the same in the mechanism. I didn't draw the mechanism here, except it's a chlorine instead of a bromine. But why don't I have to use the word trans here?
Because this free rotation, because it's a single bond.
That's right, because it's single bonds and I've got free rotation, right? I can't tell if it's cis or trans, right? Here I can, because there's restricted rotation. I can't take that 5-membered ring and completely freely rotate around the carbon-carbon single bonds, right? Right. Still in your groups. Work this problem. You never know what.
I was gonna become an artist in this class.
Yeah. I'm a bad artist.
I never knew lines and letters to be studied.
It's not the lines and the letters, it's what they represent.
And how'd you do that? I did the same thing.
I just made that.
Yeah, so you just added like
I need it to but that's wrong.
All right, folks, what's the product going to look like?
One bromine branching on top, and one bromine coming off that second carbon.
Okay? So we're going to have a bromine here and a bromine here, right? How would I name that? What's the parent?
Butane.
Yeah, so this is a butane. How would I number?
One at the top row.
Okay, so now how do I name it?
Just have terbutyl.
Well, remember, this is now part of the chain, right?
Then 3,3-di. But the butyl, okay, so 1,2-dibromo.
Okay, so 1,2-dibromo,
3,3-dimethyl
3,3-dimethyl
butane.
butane. That's right. 1,2-dibromo, 3,3-dimethyl butane. Why did we put dibromo before dimethyl? They both start with D.
It's the B and M.
The B and the M. That's right.
What happens if you circle, if you include the parent chain and the substituent coming off the bottom?
Okay, let's do that. Well, let me redraw it. So you're saying, what if this is our parent chain?
Yes.
All right, now name it.
I've done practically the same thing, but I said isopropyl.
No, it's not an isopropyl.
Is that not what's the,
Remember, this carbon is part of the chain. So all of this is taken care of in butane. And in fact, you'll find that it's still 1, 2, 3, 3. So it's 1,2-dibromo, 3,3-dimethyl butane. Didn't matter which one of these you picked to be your longest chain, you would end up with the same name.
so the isopropyl is just whenever another carbon's coming off, then it be,
This is not an isopropyl. This would be an isopropyl.
right, yeah,
There's my longest chain.
yeah, okay.
That's an isopropyl.
That's what I was.
But that carbon there is part of the longest chain, so it's not part of the substituent. That carbon is part of the substituent. Does that make sense?
Does it matter the capitals in there, like for dibromo and for butane?
I'm not going to grade you on that. I mean, I'm bad about capitals and small letters. I have trouble writing small letters. All right, so that's what you ended up with, right? And we just named that, so good. Now do this in your groups. What do you mean so long?
The first line, when you're with the first, the associations that stick out that way.
This one?
That's, yeah, why is that line so long?
Actually, these lines are all the same length. It's just the angle that's I think making you think that one's longer than the other. Yeah, so this is a CH3 attached to this carbon. This is a CH3 attached to that carbon, then that is a CH3.
Okay. I'm thinking it's.
So the way that we just drew it on the board, but back to the bromine one that we just did, would both drawings be correct? Like how we just drew it? And that one?
This and what I just drew are the same thing, yeah, because remember, there's free rotation around all the carbons. All right, folks, what do you think the product is? Tell me how to draw it. What do you think it's going to be?
Hydrogen is gonna be at the top carbon,
Okay?
and the bottom carbon gets the OH.
All right, so you think we're going to add H and OH across that carbon-carbon double bond, and we're going to get a something that looks like this, right? There's H, and there's OH, right? How would you name that?
3,3-dimethyl.
3,3-dimethyl,
Is it 2-butanol?
2-butanol. We haven't gotten into the naming of alcohols yet too much, but it was introduced a little bit in one of the chapters, I think chapter 1, chapter 2, where we were talking about that. So yeah, that's a 2-butanol molecule, okay? However, I have a magic microscope in my up there on the fourth floor in our lab. I can actually run this reaction and I can go take a look and see what the molecule looks like. And in fact, it doesn't look like this at all. It looks like that. Shocker. What is different about the molecule that I drew there versus here?
The alcohol group is on that substituent, like the middle one, that we talked on or review it.
Okay, so you're saying that this alcohol is on which one of these carbons?
That, the third one?
This one, right?
Yeah. And
Yeah.
it's not where the double bond was.
And it's not where the double bond was. It looks like we added H here and OH there, doesn't it?
And the methyl moved.
And the methyl moved, right? So we had CH3s that were only attached to this carbon, right? And now we've only got 2 of them. So it looks like a methyl group moved as well, right? And so my question to you now is why? Why wasn't it simple and it just added water across the carbon-carbon double bond? And the answer is because it goes through a carbocation mechanism. And carbocations are unstable and they can rearrange. There's only one thing that I ever tell people is absolutely for certain in organic chemistry. And that is if a carbocation can rearrange to a more stable carbocation, it will. Okay? Why did that not happen here? We had no carbocation. We had that bridged polonium ion, and that halogen contained the positive charge. There was no positively charged carbon. In this mechanism, when we draw it out, let's look and see what happens. So let me draw out the alkene. We've got water. We've got a little sulfuric acid. And I always think of sulfuric acid in water as H plus and HSO4 minus. It's a strong acid. Strong acids, when we dissolve them in water, they completely dissociate. Okay, you might remember that. And so what happens is the alkene reacts with the acid. This is the Lewis base. This is the Lewis acid. And I get, so I'm going to put my hydrogen there. Comes from here. That puts a carbocation on that carbon. I have water still around. And I have HSO4 minus. Okay? What kind of carbocation is that? Is it tertiary? It's secondary. How do I know it's secondary?
Connected to two other carbons.
Because it's attached to that carbon and it's attached to that carbon. So this is a secondary carbocation. Secondary carbocations can form, but they're very unstable. Anytime you see a secondary carbocation, you need to say, stop and think. Can this rearrange to a more stable carbocation? What would be a more stable carbocation?
Tertiary.
Tertiary. Right? We can't have quaternary. You can't have 4 bonds to carbon and a positive charge.
Yeah.
Okay? So how can I get a tertiary carbocation? I can move one of these methyl groups from there to there. And when we draw this out as a mechanism, I always use a curlicue error, which means rearrangement. And so I'm moving this carbon-carbon bond to here, which will give me so that's that carbon. There's the carbon that was my carbocation. There's the methyl group that I moved. And since I moved these electrons, this carbon now has the positive charge. What kind of carbocation is that? Tertiary, which is more stable. Now what happens? Remember, I still have water, and I have HSO4 minus. Now what happens?
The H2O breaks into the H and
Okay, think about that. You're close. I've got water around and I've got acid. Am I going to make OH in the presence of OH minus in the presence of acid? I'm not.
dissociate.
It won't dissociate, right? The acid is already dissociated. So since it's acidic, I know I'm not going to have any OH minus around because that's a base. But I've got water around. And water, the oxygen atom has lone pairs of electrons. It's actually the water that attacks the carbocation. And when that happens, you get this. And I'm going to draw it out here for you. Okay, that's that carbon, those carbons, that, right there, and there's the OH. It's or OH2 plus. Is that an alcohol?
Not yet.
Not yet. Remember I said that sulfuric acid, I only needed a small amount of it? It's catalytic. What does it mean to be a catalyst?
Doesn't get affected by the reaction, but it speeds it up.
It speeds the reaction up, very good, but it doesn't get consumed in the reaction,
That's what I mean.
right? So it looks like I consumed it here, so I got to generate it again, right? HSO4 minus comes in, reacts with that. I get my H2SO4 back, plus I get the alcohol product that I've drawn up there. Okay? Rearrangements will cause you to go crazy. They are difficult to see. They are difficult to manage. So what am I going to do? You will have, I think you have 1 or 2 homework problems on rearrangements. I might put a question on an exam that's pretty simple and straightforward like this. I am not going to give you an overly complicated rearrangement, okay? You just don't need to know them as well as I need to know them because I do that kind of work all the time. Okay? But I want you to know that they exist. Okay? So yes, we're adding water across a carbon-carbon double bond, but since it goes through a carbocation intermediate, it can rearrange, and it makes it look like we're not adding water across the carbon-carbon double bond. Okay? So the take-home message is, the reason that nothing happened like that in the top example, we didn't have a carbocation, so nothing rearranged. The bottom one, we had a carbocation, and therefore we had rearrangements. Does that make sense?
Yes, but I'm confused about that last arrow right there, the way it's drawn out.
Which arrow?
No, the one, yeah,
This one? Okay, so
so you have an arrow from the CH4 minus from where the degree 3 carbon was to where the new water is attached?
here,
Yeah,
here,
yeah.
yep. So HSO4 minus is a base. It's not a very good base, but it reacts here to get the hydrogen back so that I regenerate my sulfuric acid.
So what's the final product? Like you just have
The final product is that product, the alcohol that's drawn up there.
So there is no, hydrogen,
The hydrogen's on this carbon, right? I showed it in this step. It got added here, and then I got the carbocation, right? So it's still there. But that hydrogen comes from the sulfuric acid, not the water. But in reality, what we've added is H and OH across the molecule. So it's the same thing as adding water to it, right?
Can you draw that last part of the reaction again with the HSO4 attacking that hydrogen and then getting the alcohol? Like the step where you get the alcohol?
Uh-huh. Yeah, so let me just focus on that step, okay? So let's look at another molecule that doesn't rearrange. Let's keep it simple. So let's say, Selena, that you start off with cyclohexene, and you put in water and H2SO4. Okay? And we know that the product is going to be this. Okay? I've added H and OH across the carbon-carbon double bond. And I can do that here because there's no way for it to rearrange. Everything that it would rearrange to is still a secondary carbocation, so no rearrangements are going to occur. Okay? Anytime you take water and sulfuric acid and you mix them together, think of that as a mixture of water and H plus and HSO4 minus. Because we know that strong acids dissociate in water to their ions. Okay? So that's how I think about it. I think about it as having H plus, HSO4 minus, and water. And so what happens here, that first step, Lewis base, Lewis acid, we've got a secondary carbocation. It cannot rearrange to a more stable carbocation, so it doesn't rearrange. Okay? Now what happens? I've got lots of water around, right? Remember, it's hard to get more concentrated than water. Anybody know what the concentration of pure water is? It's about 70, if I remember right, it's about 75 molar. That's real concentrated. A liter of water contains about 75 moles of water. Right? So it's really, really concentrated. So it's more concentrated than anything else. Okay? Now the water attacks the carbocation. There's H, There's my bond to oxygen. The two hydrogens are still around. And now the positive charge is on oxygen. Right? You all see that?
Because you use the pair of electrons to attach it to.
That's right. If I circle that and I calculate the formal charge, you'd find that it's positive. And I still have HSO4 minus around. And I know that the amount of HSO4 that was added was just a catalytic amount. And I just usually write that as cat. Okay? So I've got to get my sulfuric acid back because, like you said, catalysts can't be consumed in the reaction. But this isn't this yet, is it? It's close. All I got to do is get rid of one of these hydrogens. Put those electrons on oxygen, and I end up getting my product. Plus, of course, I get back my catalytic amount of sulfuric acid. I didn't consume it.
So because that negative went and made a bond with the other hydrogen,
Mm-hmm.
so that takes off the negative charge, makes the oxygen back to not positive. So
Yes.
no,
That's right.
and then the plus H2SO4 is still there.
Mm-hmm. Yep, it's still there. So this is called acid catalyzed hydration. And it's one way in which we can form alcohols. And it goes through a carbocation intermediate, and it can involve rearrangements. Not in this case, but it can. Okay? Does that make sense? Okay. Sure.
The only thing I'm concerned, I don't understand is like the negative charge you give air to the hydrogen to the oxygen, and because you like move that electron, does that make the hydrogen go away? Like I'm confused. Like
This hydrogen does not go away, it's now here.
oh,
Remember, this is HSO4 minus.
oh, now it's H2.
Now it's back to H2SO4 minus, yeah.
Okay.
Yep. We've accounted for everything. All right. This towel is really getting nasty. Has everybody got what they want off this?
Just one thing, back on that, whenever the carbocation rearranges, is it the, I don't know how you say this, can you say smaller cation? Well, like the secondary wants to convert to a
Tertiary.
tertiary
Mhm.
to make room for the, like the OH?
No, it has nothing to do about making room for the OH. It wants to do that because that cation is more stable. The more carbons that are attached to a carbocation, for reasons that we're not going to get into, makes that carbocation more stable.
Right.
So you're going from a less stable carbocation, which is secondary, to a more stable carbocation, which is tertiary.
So
That's just after the double bond is broken.
Yes.
Okay.
You have to have the carbocation before anything can happen. And you can't get that until you break that pi bond.
So anytime you have a secondary carbocation, if we can make it a tertiary
Do it.
carbocation, then do it.
Do it. Yep. If you can take a secondary, make it into a tertiary, do it. And you can only do that by 1-2 shifts. You can't move something from, 10 carbons down. It's got to be on the carbon that's attached to the carbocation. Yeah, something moving. All right. There is another way to add water across a carbon-carbon double bond, and it's this process called hydroboration oxidation. It's another reaction. It's a two-step reaction. In the first step you take the alkene and you react it with, and I'm going to put it in air quotes, BH3. You can't buy a bottle of BH3. Okay, it's very reactive stuff, but it behaves like BH3. Okay, and we'll talk about that in just a moment. And what happens, and what's really interesting in this reaction, is at the same time you add a hydrogen and a boron across the carbon-carbon double bond. You do not make a carbocation. Okay, so a hydrogen and a boron get added across the carbon-carbon double bond to make what is known as an alkyl borane. Now, this kind of looks like BH3. It's BH2, right? It can continue to do that. It can react with another alkene and it can react with another alkene. But we're not going to get into that, okay? Just think of it as doing it once, okay? It's the same process. We make this so-called alkyl borane intermediate, okay? You can actually bottle these. They're intermediates that are fairly stable. They are reactive. You've got to be careful with them, but you can put them in a bottle. And then in the second step, we add hydrogen peroxide and a little bit of base, like sodium hydroxide or potassium hydroxide. You need basic hydrogen peroxide. Where do you all know of hydrogen peroxide? What do you all use hydrogen peroxide for? Pardon? Stain remover? Yeah, I guess some have stain removers have hydrogen peroxide in them. It'll bleach colors out. Yeah. What else?
Most people, wounds.
Wounds, right? You might buy a 3% solution from Walmart and pour on there on a wound and it bubbles, right? Typically, that's what you all can buy. You can go to CVS, Walmart, or wherever. You can buy a 3% solution of hydrogen peroxide. Where else might you have come into contact with peroxide? If you like to bleach your hair, people will use peroxides, okay? So you can, if you go to the salon or whatever, right, they might use a peroxide solution to lighten or to give you highlights in your hair, okay? So these are very powerful reagents. They do a lot of work. They do a lot of things, okay? Now, in organic chemistry, we don't go to Walmart and buy a 3% solution. We actually use 30 or 50% solutions, which are very reactive. And in fact, even when I open the bottle, you have to be careful, because if I'm not wearing gloves and you get a little bit on there, it will make your skin turn, deathly white looking. It oxidizes so rapidly. It can hurt you, okay? It's not like the 3% solution, okay? But what happens when you add this is wherever that carbon boron bond is, the carbon boron bond gets replaced with the OH. So this is called the hydroboration step. This is the hydroboration step. Think about that name, hydro for hydrogen, boron, borane, right? So we're adding H and B across that carbon-carbon double bond. And in the second step, we're using peroxide, which is an oxidant. And so that's where the oxidation comes from, okay? And so it oxidizes that carbon boron bond and makes an alcohol. Now, you all should be saying, why in the world do we need two reactions to do the same thing? Okay, I'm going to tell you why we need two reactions to do the same thing in just a moment. Because it depends on what kind of alcohol you want to make. Okay? Now, like I said, you can't just buy a bottle of borane, of BH3. They make borane and they put it in solution with this molecule called tetrahydrofuran. You don't need to worry too much about that. But borane is a Lewis acid. Boron does not have 8 electrons around it. It has a vacant p orbital. And so it's a Lewis acid. And of course, THF, the oxygen, has lone pairs of electrons. So it can function as a Lewis base. And it makes this molecule that we call the boron or borane THF complex. Okay? You can buy this in a bottle. Okay? It's very stable. It's easy to work with. But when you put this in solution to do hydroboration oxidation, all you have to think of it as BH3. Okay? That's why I said air quotes. Just think of this as BH3. Because in solution it will dissociate into both of these a little bit, and that's what does the chemistry. Okay? Little history, borane chemistry won some Nobel Prizes back in the day. It's very, very important. Borane chemistry was the hot topic maybe 30 years ago, maybe even a little longer than that, maybe 40 years ago, because the federal government got interested in powering high-flying spy aircraft with diborane. And there's actually a famous book out there called The Green Flame. And they were going to use that as a fuel for these high-flying jet aircraft. to spy over the Soviet Union, et cetera, et cetera. It would have made an excellent fuel, except that the flame that came out the back end was a brilliant green. So all you needed was a green-seeking missile. You could kind of follow the plane pretty easy. But anyway, the government spent a lot of money. Boron became cheap, and so chemists got involved in doing a lot of boring chemistry. And so, did I say boring or boring? Not boring, boring chemistry.
So would they use that? You said it was an energy source?
Yeah, they were going to use it as a fuel. Yeah, they were going to use it as a fuel.
They were or they do now?
Huh?
They were or they do now?
They don't. It never really came to fruition. It was a research project, but they spent tons and tons of money on it trying to figure it all out. And at the end, green flames coming out the back of your jet just turned out not to be a great way to go. So if you think about it, right, we're breaking a weak pi bond again, and we're getting two strong sigma bonds, just like we've done in a variety of things, right? The thing that's interesting about this is that the hydrogen and the boron get added at exactly the same time. There is no carbocation. Since there's no carbocation, there can be no carbocation rearrangement. So number one, that's a reason to do it. But the hydrogen, since we're dealing with this, actually the hydrogen and the boron are added on the same side of the alkene, right? So very similar to the first halogen, if you will, in making that halonium ion. We get this so-called syn addition, okay? And now all we got to do is oxidize it off, right? But here's the thing that's really cool about it. If we took this alkene that's drawn right there, and we did H2O and H2SO4, what alcohol would I get? I would get 2-propanol. I would get rubbing alcohol. If I do the hydroboration oxidation sequence, because the boron is on the least substituted carbon, which alcohol would I get? 1-propanol, right? So if I do BH3, H2O2, hydroxide, I end up with 1-propanol. This is why we have two ways to make an alcohol. Because if I want to make 1-propanol, this method won't work because it goes through a carbocation. So I got to go through a mechanism that doesn't go through a carbocation to get the 1-propanol. Because look, the boron goes to the least substituted carbon. Okay? So, we call this alcohol.
So what do you think these substituted is? So the hydrogen doesn't go into the one with the more hydrogens?
Nope. Notice where the hydrogen goes here.
So
The-
it doesn't follow the Markov rule?
It does not follow Markovnikov's rule. That is right. The hydrogen goes to the other carbon.
And that's
Remember,
why-
Markovnikov's rule only works because there's a carbocation. There is no carbocation here. Okay? So this, we would say 2-propanol made this way, we say it happens by Markovnikov addition. It follows Markovnikov's rule. This mechanism does not involve a carbocation, and we say that this is an anti-Markovnikov addition. Okay? And so you end up, wherever that carbon boron bond is where your carbon oxygen bond is going to get. Don't worry about the retention of configuration. We'll talk about that in chapter 6. So if you wanted to make 1-propanol from this alkene, you can't use the top method. You got to use the bottom method.
Number 2 right there, H2O2, is that an I? There's a line over there.
No, that's a slash. H2O2 and sodium hydroxide is what that slash means. Yeah, you think of it that way. It's got to be basic.
And those negative? That has a negative charge?
The OH?
Yeah.
Yeah. I mean, it would be sodium or potassium hydroxide, but it's the hydroxide that you gotta have, so I just abbreviated it as OH minus. Okay? All right. Break up into your groups again. Work those 4 problems that are listed there. So what products would we get from doing those 4 different reactions on that one alkene? Not at the same time, right? If I took this alkene and I reacted it with bromine, what would the product be? If I took this alkene and I reacted it with water and sulfuric acid, what would the product be? So on and so forth. Let's take 5 minutes. Work them out.
Do we need to name all of them?
No, you don't need to name it.
Would you not add it on top of that? Would you add it like on the same bond but on the side?
Because this is a methyl acetal.
Okay, so you just kind of like, it's attached to the same base carbon, I guess, but it's just like kind of like another offshoot on it rather than adding it on top.
Yes,
Okay.
yeah,
Okay.
yeah, it won't be on the carbon that didn't initially have the double bond.
And the same would go with this one too. You just kind of don't touch that.
Right.
Okay. That's something I always kind of trips me off, is when you have like an offshoot or
Yeah.
do I leave them alone? Or do I do something with it? Or? That makes more sense.
So it's like, this bond, in the middle of the bond,
just,
So that first reaction mechanism, yeah, that he does.
About 1 more minute.
and also, H goes to carbon and H has.
So it would be this the bottom or?
Basically, you notice here, this carbon, top carbon won't have any hydrogens. So argon has 4 members, this one has 1.
Okay.
So it's gonna be a different phase for the hydroboration oxidation. This is just, that's just the
All right. This is how, in my opinion, it is the best way for you to keep track of all these things. I call these road maps. So what you notice is that in the middle, I've got one functional group, an alkene. And around it, I'm showing all the reactions that I can do with that alkene. These are great ways to study reactions. You can have these, you can be watching TV in the middle of a commercial, you can just pull one out and study it. So you can study these things really quickly. So in the middle, we've got an alkene, and we've got 4 different ways in which we can add things to it. So let's start with the top, right? We're adding bromine across the carbon-carbon double bond, right? So what's the product going to be?
Two yards and this.
Yeah, I'm going to add the bromines across the carbon-carbon double bond, right? So I'm going to have that bromine, and that bromine. And they're going to be trans to one another, but I didn't draw it in, okay? We'll talk more about stereochemistry again in chapter 6. I can add water across the carbon-carbon double bond using sulfuric acid and water. What kind of alcohol am I going to get?
The alcohol would be, the hydrogen would be where it follows the carbon.
Yep, so I end up with this alcohol. And I would, if I was putting together my roadmap, I would write out to the side something like Mark, so that it would remind me that it's Markovnikov addition. Okay? Going down, adding HCl across the carbon-carbon double bond. What's the product that I'm going to get?
Just the HMCl and follow the carbon.
Markovnikov again, right? So again, I would write Mark. And then here, I've got the hydroboration oxidation sequence under basic conditions. What's the product going to be?
The opposite of the mark one?
It's going to be opposite of what we have there, right? So I'm actually going to put the hydrogen there, the OH there. I end up with an alcohol, and I would write anti-mark. Okay? Now, we're not quite finished with chapter 5 yet. We're getting low on time, so I'm going to skip this for today. We'll pick this back up on Monday and then get into chapter 6. If you have a model kit, please bring it for chapter 6. If you don't, I'll try to remember to bring some more model pieces with me. Okay? We're a little bit behind on quizzes. So I need you all to turn in problem 4.15 from chapter 4. Please place your name, ID number as you've done in the past.
Sorry, problem number
4.15, 15, 415.